Okay, well, thank you, David, and a warm welcome to all 30, however many we are at the moment in the audience. Yeah, this evening's presentation is to be given by Miles Postlethwaite, and the title I have is Hydro and Wind Generation Systems. So I think it's probably, I'll leave it to Miles to sort of do any more. Well, I have no more details in front of me, so I can't sort of elaborate. So I'm afraid, Miles, you'll have to elaborate as you feel fit, as you might say, as you carry on into the talk. So with that, I'll hand over to you, Miles.
Oh, thank you, Simon. Well, it's an honor actually to be asked to speak to you. I'm not used to, I've never done a Zoom meeting before, never even participated in one, so probably go wrong. And I say we have 36 participants. I'm just wondering how many of them got a drop off as we go through. Anyway, we'll see. If there's any left at the end, it's a success. Right, I'll make a start. Okay, my name is Miles Postlethwaite. I've already been introduced. The contents of what we're going to do roughly. I'm going to give you a quick intro, what a hydro system consists of, how we process an initial inquiry, turbine types of connection, generators, case study, Q&A. But as Dave said, by all means, chip in with questions along the way. I probably prefer that anyway. Border Hydro is a small company which supplies and installs wind and hydro systems. We used to be nearly all wind until about 10 years ago. Now we're nearly all hydro. The loss of the feed-in tariff affected that a lot. So we're going to I think we should call it micro hydro and small wind. We never put any massive systems in. Micro hydro is anything I would say under about 200 kilowatts. And biggest one we've put in is about 140. And we go right down to very small. If you've got an off-grid house, even a few hundred watts is helpful if you've got nothing else. So what's a hydro system consist of? To make a hydro system, it's a turbine and whatever it needs to drive it. You're taking energy out of a river. So we've got to get the water out of the energy, out of the river somehow. An intake point. This is a generic drawing I got off the internet. It's not quite how we do it, but find a way getting the water out of the river, throw a settling tank down a pipe to build the pressure up, bring it down the hill till you got the maximum pressure possible by putting the turbine in as low as you can, pass it through the turbine and pass the spent water back into the water course. I think you probably all know that. It's not very complicated. Right.
Miles, typically you say you've got some pressure there. Typically, yeah. What sort of pressure do you have at the turbine?
I was going to come on to that. The reason I didn't elaborate on that because there are high head and low head systems. I'm going to come on to that in a minute. So in this particular, I don't know what height that looks at. It doesn't give you any height really, but maybe there's 150 feet there. But I'll bear what you said in mind, but I'll come on to it in just a second. We're getting an inquiry. Obviously, this is a normal stuff you go through on the phone. We do a site visit. If somebody rings up, they've got a river or a stream or something, can they have a hydro? I want a 7 kilowatt turbine. You can't give them a 7 kilowatt turbine. We don't know what the side of their turbine is determined by the resource they've got. If they've got a little stream with not much head, they haven't got 7 kilowatts. So I have to tell them that. We'll do a site visit if they ask us to, and then if necessary, a feasibility study, which assesses the cost of the system and whether it's viable and whether the Environment Agency is going to let you do it. The things we ask them, first of all, to know whether you've got a viable system, we need to know the head, the flow, the length of the pipe. The head is the vertical distance between the point where you take the water out of the river and where you want to put the turbine house. Now you want that distance as great as possible. you know, the higher the distance the water's falling, the more power you're going to get. So it's, to work out power, it's a product of head and flow. We need to know how many liters per second. We'll multiply that times the head. If we have those two, we know what sort of power is available, but it doesn't mean the system is necessarily viable. We need to know what the length of pipe's going to be. In other words, how far is it from the high point when the river comes onto your land and the lowest point where you expect to have the turbine. If it's 1.5 miles, it's not viable because the length of pipe is going to be horrendous. The amount of friction in that pipe is going to take all your head away because the friction reduces your head. Also, the longer the pipe, to reduce the friction, you have to make the pipe wider. So we have to take the water through slower to reduce the friction or the drag, if you like, the longer the pipe. So we're all right up to about, normally up to about a kilometer. You know, it's viable. Much beyond that, you've got to look at it hard. These are the other things: feasibility, court, environment agency. Those are the people you have to go through to get a license to abstract the water. Now, you've got to have a license for this. Even though you're taking the water out, you're putting it back in. They count it as an abstraction because you're, the bit in the middle is called the depleted reach. They don't want you to dry that up because of the various wildlife, the flora and fauna in the river. So they'll tell you what you can and can't have. Well, actually, they don't tell you what you can and have. You have to ask for what you want, and they'll say yes or no. They make you guess it, really. One way of working out the flow, which is the hardest bit, is to put a V notch in. I don't know if anybody's familiar with this, but basically, if you put a little dam, a small beck, creates a pool above behind the dam like this. So this is the beck coming through here. You put a little dam across, so it stops the water and it gives you a calm pool. And you put a right-angled V in the bottom. Now this, by the way, has to have a sharp edge on it to be accurate. So you either nail a bit of tin along here on the inside or the outside, or you get a chainsaw and you sharpen it off. Then the water flows through the V. You've got to, I couldn't tell you what size to make the V. You've got to just try it and see what happens. Get the water flowing through the V so it isn't coming to the top, but it's just sort of nicely coming through. And what we're trying to do, we're trying to measure the vertical distance between this point here and the level in the pool. Now, why don't we just put marks up here, calibrate some marks up here? Well, you can't do that because as the water reaches this dam, it starts to slope off. So you're going to get a false reading. So you have to reference this bottom of this notch, dead level back to a point underwater, and you stick a stake in with calibrations on it. You mark a 0 point in there. So this is 0. Where it breaks the water, that's your equivalent to how much of the notch is occupied, and that's accurate then. Now, if we know that, there's a calculation we've got to actually put it into a program on the computer where you just type that. It'll tell you instantly how much water is coming through. I say do this, not many people will do this because it's a bit pointless nowadays. You've got to do it. You really need to do that for 12 months to get an idea of what your flow is. And if the Environment Agency is going to let you take water, they need to know what your flow is. There's a company down in Oxfordshire which will, if you give them the grid reference of this offtake point, they can do a computer study based on the size of your catchment, which they'll work out, they'll do it all. And they also work out using known data in the area, which is from gauging stations. They compute it, taking into consideration the size of your catchment and the amount of water you can expect. They usually are accurate to within 10%. They're pretty good. And if you want to get if you go to the Environment Agency to get an abstraction license, they'll want to know how much water you've got. If you submit this, they'll say, okay, but we're not just going to accept that. We want 1 or 2 spot readings just to calibrate it. And they're usually pretty close. So I would always recommend people to do that. Also for your own benefit. If you want to put a hydro system in, no good kidding yourself, you're going to get 25 kilowatts when there isn't enough water there. This happens to be an intake. I'm just going to show you this now. This is one that's installed. I've got this slide later on as well, because I'm going to show that I think we've dammed across the river here, the beck rather. And you can see they've created a pool back here. This wasn't there before we put this, obviously. Now this is the water intake. We have two things here. The water comes over this, down this screen. This is a wedge wire screen, Quanda screen. I don't know if you're familiar with it, but being engineers, you probably are. It's triangular wires set absolutely flat across the top, but very razor sharp edges. So the gap is about 1 millimeter apart horizontally. And then as you go underneath each bit of wire is shaped like that, so that the gaps increase as you go underneath it. As the water comes over, it comes down the screen over this accelerator plate, which is a curve which reduces the pressure in the water. It speeds it up basically and sucks it onto the screen, so it doesn't sort of overflow it. And then the water comes down, it gets shaved off like a cheese grater down here. Any debris sort of stays on the top. If debris starts blocking up too much, the water will come and just shove it off. So it's self-cleaning. They're quite expensive, these, but they're very, very well worth it. For a high head scheme, this is what we'd always use. Another thing you also can see here is I think you can see this is a little V notch here beside it. That's the shape of it there. This is what's called the compensation flow. The Environment Agency, when they allow you to take the water, they don't want you to take it all. They'll say, well, maybe want you to leave 5% in. And that'll be specified how much water you have to leave behind. So you put this V notch in, which is lower than this intake. So this will always get it. When there's not enough water for this will get the water first. Only if there's water on top of that can you have some for the turbine. And now we have to do a mimic flow as well, which is, you notice these sides become parallel at the top of the V. This is a V here, and then the side becomes parallel. So if you get more water now, the turbine gets more water, but then so does the compensation flow. So it always gets a percentage, and they'll tell you what the percentage has to be. And it's quite simple to work out. If you've got 75-25, well, all you have to do is make this 25% the width of that, and it's going to work. Plus the compensation flow on top. Turbine types. High head and low head. Now, I think Simon asked the question earlier. What pressure do you want? Well, when we're assessing a site, we divide them into two categories, either high head or low head. Now, these figures, 15 meters greater or over 15 meters, under 15 meters, very arbitrary really, but it's what we use roughly. You get two families of turbines. You've got impulse turbines, such as Peltons, Turgos, and Crossflows. An impulse turbine is one which is running in air. I always like it to a kid's bike upside down when you're washing it with a hose pipe. You squirt the hose pipe on the tire. That's the Pelton, spins the wheel around, hitting the tire tread. If you squirt it on the spokes, you've got a Turgo. The water going through the side and coming out the other side. And a crossflow, well, that's a bit different. I'll come to that in a minute. But reaction turbines, low head, where you haven't got you've got plenty of water, but you haven't got much pressure. There's been an old water wheel there in the past. And the maximum head you're going to get with a water wheel is the diameter of the wheel if it's overshot. So if you had a 12-foot wheel, well, that's probably all the head you've got. So you can't make much power out of 12 feet of water unless you have a lot of water. The water hasn't that much energy in it, so you've got to have a lot more of it. And for these, we don't use Peltons and Turgos, which are jets of water hitting things. We have reaction turbines, such as a Propeller Turbine or a Francis. They're all variations on the same thing, where these are submerged in water. The Peltons and Turgos, these are running in air. These are running in water. They're completely submerged. You can imagine a propeller turbine. So these are aerofoil surfaces in propeller turbines, Francis and Kaplan. The propeller turbine, you can imagine what that is. Kaplan's like a propeller, but with adjustable pitch blades and the gates at the side. I'll come to that. Show you the high. That's a Pelton anyway. A jet of water here hitting these buckets at 90 degrees. If you look at a Pelton bucket, they're split into two halves. In the old days, there used to be just one solid bucket, one scoop. And we went to do an install at a site about 10 years ago. We replaced the turbine, which was still running from 1901 with the old type, and the guy went to the new type. These are more efficient now. The jet of water hits this split right in the middle, and half the water goes this way, half that way, and it basically hits it and turns the water around 180 degrees, comes back towards the nozzle. So it comes out like that, comes out like that. So very efficient, a Pelton turbine. These are the highest head types of turbines, Pelton usually. You work on enormous heads. They'll work, actually they retain their efficiency even if you take them down to ridiculously low heads. The only thing is, the lower the head you go with a Pelton, if you're getting below 50 feet with a Pelton, it'll still be just as efficient, but it has a low specific speed because the water's hitting these buckets on the periphery of the wheel. The speed of the water coming out of that nozzle at less than 50 feet is not that fast. So you can imagine if you're doing whatever speed it is at 50 feet, this diameter is going to go at the same speed as the water when it's freewheeling, and when it's going under full load, it'll be about half that. Now you've then got if you've got the thing's going to be pretty slow. So unless you've got a very slow speed generator, you're going to have to gear it up a lot, and that's not clever. Also, once you start running a Pelton very slow like that with low pressure, it's not going to be able to take enough water in to do the job. So if you enlarge the nozzle, you're limited to how much water these buckets can take. So that's why we don't use Peltons on low head. That's the Turgo. That's the top of a Turgo looking down on it. Now, I'll show you the side view of it. The water, as I said with the Pelton, the water comes in at 90 degrees to the buckets, sort of like here. But on the Turgo, they come in at 20 degrees off the vertical, and the water jets come in like at this sort of angle. They come into these veins and then out here around them, like the spokes of a wheel, if you like. A Turgo can handle a bit more water than a Pelton for the same size, and it has a higher specific speed. The reason it's a higher specific speed is because you're nearer to the center. So the same speed of water is you've got a smaller circumference to go around. So Turgos are the most popular type in the high head that we use. We would only use a Pelton, really. Well, we use whatever we can get hold of, to be honest with you. This is a crossflow. Now, a crossflow, if you look at it, this is sort of a bit of a hybrid turbine. If you look at this drawing here, on the left, the water's coming here from the left, and the runner inside a crossflow is like a big sort of almost like a water wheel within it. The water comes through the veins. About 75% of the power generated by a crossflow comes when the water comes through the top into the wheel. It comes into the middle of the wheel. Then it goes out again through the bottom, gets a second hit, about another 25% of the power. So it's an impulse turbine, although it has a draft tube on it, like a reaction turbine. I'm going to come across, I'll talk about that in a minute. Low head, this is a Francis turbine. This is where the water comes round here, around a scroll case with the reducing diameter till it goes through the runner in the middle. And the runner, Francis runner, looks like that. That's it on a horizontal, but if you imagine that on his end, the water comes through these veins, and it comes through all the way around, a jet in it. The water's guided with guide veins, which aim it into these veins all at once, all the way around. Hence the scroll case. So you're trying to keep an even pressure of water, because as it's taking water out as it goes around, you don't want a great void where the pressure is reduced. So we we tighten it up as it goes round, keep it going. Once it's been through the turbine, it comes through a draft tube. This draft tube, the bottom of it, is itself underwater to maintain a vacuum. And the weight of water coming through here sucks on the runner above it. So you can actually, with a reaction turbine, like a Francis turbine, you can use every inch of head from the surface of the water where you took the water to the river where you're taking it back, because you don't waste anything. Whereas with a high head, you've got to park the turbine above the river and let the water back. That's the Francis runner. That's a propeller turbine. Fairly obvious what it is. Water comes through guide vanes. These guide vanes actually serve to spin the water round, get it rotating first before it comes down through the propeller turbine. And a Kaplan turbine looks very similar, but it has variable pitch blades, and the guide vanes move as well. They're sort of linked. They're extremely expensive, not something we'd use a micro hydro. I've skipped a lot of stuff there because of the things now. Yeah, if we go back a couple here, I'm going to talk about the cross flow again. Look at this cross flow. I don't know if you can see all of that, because I think you can, yeah. Right, the nozzle in the cross flow, you see this green thing, that's the nozzle, and that's in the open position. So the nozzle's almost touching the wheel there. When that pointer is touching the casing, the nozzle's closed. It doesn't let any water through. And as you can see here, in this one, the water's coming from the right across to the left. So it's the opposite way around to what the drawing is. But the nozzle is behind this plate here, and you can see the arm there on the end of an electric actuator. The nozzle's closed at the moment because the actuator is extended, so the nozzle is hitting the casing there. When it's running, these crossflow turbines have a draft tube as well as the Francis and the propeller. Even though it's an impulse turbine, suction does help. And if you look on the side here, there's a little ball valve with a plastic pipe. Now that plastic pipe, we put it in drop it into the water, and we turn this valve on enough to let water, using the suction that's in the casing, to pull water up as far as it'll come. And we want the water level to stay at about the level of the bottom of the casing. In other words, the top of the draft tube. So we want the water level to come right back from the river up, but not quite touch the runner, because it'll foul it. Then you've got the most weight in the draft tube causing the most vacuum on there. And you can, if the water's at the wrong level, you alter this, you open this ball valve here, which lets air into the casing. So it reduces the suction on. So you adjust that, you crack it open to where it gives you the right water level, then you leave it. Actually makes quite a noise. It's quite a noisy turbine, and this thing with its sucking makes a lot of noise. So we normally have a kind of a sponge damper in there, which keeps it quieter. So that's a cross flow. And we don't use, well, cross flows, they're an impulse turbine, and they can be used on a range of heads, but we would tend to use them on low head. Otherwise, we'd use a turbo, because they're not quite as efficient. They're very low speed, very low. You nearly always have to gear a cross flow by putting belts on it. You lose power doing that, and belts wear out, etc. Right, so that going on to types of connection and generators. Right, so we get the power. I've really missed out pen stocks, but I should go back to them shortly. We'll put a generator on to the choice of generators, actually, choice of type of connection. Most people want to be grid connected. When I say grid connected, connect into their side of the meter. Power that goes in will first go into anything they've got switched on. Sorry, excuse me. Any excess will go back through the meter, and we put an export meter on. They can get paid something for it. That's a grid connected type, and we'd normally, for that, we'd use an induction generator. If you're not familiar with that, that's like the same motor as you'd have on a conveyor belt or all kinds of, the most common motor you'll find, squirrel cage type motor, basically one of those. If you run one of those as a motor, 4-pole one run about 1500 RPM. If you then put a device on the end of the shaft and try and run it faster than it was already going, while it's still connected, it will start pushing power back into the mains. So it's, if you drag power out of it, if you slow it down by putting a load on it, it sucks power out the mains. You speed it up, it pushes power back into the mains. It'll also resist you as well. It won't want to go faster than 1500 RPM, but it will a bit. But it'll push power in. So very useful that way. They're also bomb-proof in terms of overspeeding. Another type of generator we have used in the past is a synchronous generator, which is the sort of generator you get on a diesel engine or the back of a tractor for standby. They're your conventional generator with copper windings, and they're very good. They're very efficient. They have a downside with them in that if that turbine takes off and overspeeds for some reason, you'll blow the thing apart. The windings will fly out and hit the stator. So any we do use, they're specially bound with extra strong bindings on them, and we have to govern the turbines very carefully. The third type of generator we use quite a lot of is Pmgs, permanent magnet generators, which have become popular because of the neodymium magnets you get now. They're very simple. They're just very, very strong magnets with coils of copper wire, going past coils of copper wire. We don't have any iron in them, because there's no need to be, although the magnets are all backed onto iron, but there's no iron core, which reduces cogging, which makes them easier to turn. But they're very efficient and quite simple, but they're not cheap. And if we use them, because they're going to produce 3-phase AC, we have to put it through, to rectify it and put it through an inverter to be used either in a battery or back into the mains. And those types of generators we use in wind turbines all the time, small wind turbines, because they can be direct driven. You can make a permanent magnet generator with a big diameter, axial flux, like big wheels, and they can go, a couple of hundred RPM or less quite happily and still generate your power. Whereas the conventional mains type of generator wants to be going about 1500. So that's the advantage of induction of Pmgs. We use them in off-grid situations where we maybe have batteries. Where we have slightly bigger systems, we don't use batteries. But any questions on that so far?
I've got a question, Miles. Where you've got those the mains generator types, how do you control the frequency of the voltage coming out and control the voltage?
Right. I'm really glad you asked that question, because I wanted to find a way of getting into that. Yeah. The grid connected turbine, there's actually more than one way of doing it. The conventional way, with the bigger ones, we'll run the turbine, we'll spin this thing up dead, just physically spin it with water. So the turbine will drive this dead motor up to, and we have a speed sensor on it, on the shaft. And when it gets up to just about dead on 1500, we switch it on as a motor. But because we're running up to speed, we're not really taking any power out of the mains. There's no big shock on the mains. So we switch it on as a motor just as it gets to that speed. So there's none of this great big thump on the mains when you switch the thing on. It still is a bit. And then as the turbine passes through 1500 and starts to increase, it'll take it up to 15, 20, 15, 30, and then you're on to probably full power. The frequency, because these induction generators are not synchronous, in other words, actually the speed of them is not governed by the frequency of the mains. Even though I said they go 1500 RPM, it sort of wants to go that speed, but you know yourself, if you have a lot of experience with them, is that when they're running under load, they're only doing about 14, 20. And as generators, they can go well over 1500. So they're allowed to slip. They get slippage. That's what makes them useful. So the frequency is not a problem. the mains is the governor. The mains is like a great big brake. The more you try and speed them up, the more the mains will resist you. But the energy that you're putting into it goes back as electricity into the mains, but it doesn't go back as really increased speed, not very much anyway.
Right, so there's no need to control the flow of water. It sort of works itself, sorts itself out, is it?
Yes, we put a generator on which will handle the maximum power of the turbine plus a bit. So if you have a 50 kilowatt turbine, we put a 50 kilowatt or a 55 or a 60 kilowatt generator on it. So no matter what the turbine does, it can't drive it too fast. If we, in a low water situation, we're only getting 10 kilowatts out of the turbine, you will get 10 kilowatts out of the generator because it still drives it at the same speed. The turbine, even when there's low water, the turbine still goes exactly the same speed because the water's still falling from the same height. And that brings me on to something else. Why is that the case? Because we only run the turbines with the pipe full at all times. If there's no air in the pipe, it's full right back to the intake. And at the intake, where I showed that intake before, that was a washover screen where the water comes over the dam, over the screen into a tank. And inside that tank, we have a level sensor. So it senses the level of water inside that tank. Obviously the water goes out of the tank down to the turbine, but if the water intake, the water supplies become less, so that the turbine is actually taking more than what's coming in, the level of water in that tank is going to decrease. The level sensor tells the turbine to start closing down a bit until it evens up the level. We have a thing in the tank, we call it a head aim, an aim level, and a level inside the tank where an arbitrary nominal level where we want the level to be. If the water goes below that, it tells the turbine to close down somewhat. If the water goes above that, it lets it open up. So it's always trying to keep it at that level. So it's the first sort of point of contact for altering the power going into the turbine, but it's not like a governor which controls the speed. The mains does that automatically. It controls it, you cannot alter the speed of the mains by putting power in. It doesn't matter how much you've got, because whatever you've got, the power station is far bigger than you. So you can upset the voltage, but you can't upset the frequency.
So in effect, you are, depending on the flow of water that's available at the head, you actually are adjusting a valve to use as much of that flow as possible, but still always maintain the same head and same pressure coming out of
Yes, effectively what we're doing is, imagine that was a hose pipe coming off a tank, and you put your finger over the end of the pipe to make that jet of water hit a point on the wall. Now, if that jet starts to come down the wall because there's less pressure, you stick your finger harder over the end of the pipe to get the thing back up to the point on the wall, if you see what I mean. So we're putting our finger on the pipe at all times to keep the pipe full right back to the start. Sometimes that means we're only going to trickle out of it, but we're still, as long as that water is full, goes right up to the intake, then however little water that's coming, it's still going to be doing the same speed when it hits the bottom, because it's root GH. It's root 2GH, that's right. Twice gravity times the head, square root of that, will tell you what speed that water is doing when it hits the nozzle at the bottom. And it doesn't matter how much water it is or how little, as long as it's coming from that height, it'll be doing the same speed. And that's also how we size a Pelton or a Turgo. We size the wheel, because every turbine we put in is different. Even what they look the same, they're actually different, but the different size runners in them. So if we know what somebody's got a certain head and flow, we need to keep a certain amount of water going through. So we have to work out, first of all, what speed the water is going to be doing when it's hitting the nozzle. So from memory, I think if you have 100 feet water starting 100 feet up, 100 foot ahead, time the water is coming out the bottom, the nozzle is going to be doing something like 24 meters a second, somewhere around there. So if that's 24 meters a second, then that's, and remember on a full load, it's going to be 24 meters a second is the speed of the circumference of that turbine when it's freewheeling. Obviously, because it's going to be hitting the buckets away at 24 meters a second. So you work out what that is in terms of rotation of that turbine. And then when it's under full load, it'll be doing about half of that. So if you have a turbine with a circumference of 1 meter, it's going to be doing 24 revs per second freewheeling. And then when it's under full load, you'll be doing about 12 revs per second under full load. So we work out, and then because to avoid things like belts and extra bearings and seals, we like to mount the turbine runners like Peltons and Turgos right on the shaft of a motor. Sometimes we get modified shafts, but that's just use the bearings that's in the motor itself, mount the thing vertically. So then we want to size it so the thing's doing about 1500. Now, if we can't do 1500, we'll try 1000, get a 1000 RPM generator or and that. So we can alter the circumference of the turbine, bigger or smaller, to get the speed we want. The other thing is also we need to be able to handle the amount of water. You can put 1 jet, 2 jets, 3 jets. I don't really like 4 jets, but you can do it. You lose a little bit of efficiency when you get to 4 jets. So there's a limit to the amount of water that each of these runners can hold. So a Pelton, for instance, the maximum jet size that you want on a Pelton is something like 11% of the PCD. So that's maximum jet size, not maximum nozzle size, because the jet's actually smaller than the nozzle. Because the jet contracts after it's come through the nozzle. It's called the vena contractor. So to a point where the minimum level length starts to increase again. So I'm sorry, I waffled on there a bit.
That's okay. We've got another. While you're just talking about efficiency there, one of them, Jim Lyons, has asked what sort of efficiency is a turbine?
Right. It depends on the turbine itself. Various turbines, the Peltons and Turgos are pretty efficient. Depends who's making them as well. We're into the 90s with the turbine, but if we always talk about water to wire efficiency, because the only thing that matters is the energy you get from the water once you got into the wire. So we have to take into consideration the generator and any transmission there is there. So we want to find out what we get there. We usually work with micro hydro. If we get a good system and anything above about 15 kilowatts, if we get it right, we can get up to around about 70% overall efficiency. And below that, 65% or 60%. Once you get the very small ones down to about a kilowatt, you're down to 50%. And I don't worry too much about efficiency. The main thing you want is, the water doesn't cost you anything anyway. The main thing you want is a reliable turbine. And one of the biggest, well, the biggest thing that constrains us is the lack of availability of turbines. We do make some of our own, but we also buy, mainly we buy turbines in. And we have a heck of a job getting turbines, especially now.
Why is that? Is there just a lack of suppliers?
Lack of suppliers. The feed-in tariff, when it was going, it started, it cut out about 2 years ago, and it started decreasing from 2012. But when the feed-in tariff there, it was a great encouragement for small companies. There was 1 or 2 companies I can think of right away started making turbines. The cross-flow turbine I showed you there was made by a company in Devon, really well-made turbine. Good company, doing an excellent job, superb job, and very reliable, really well built. But he's stopped building now. He says by the end of this year he doesn't want to build another one because there's just the market's gone. And same, there was another company in Wales doing little Turgo turbines, and I don't know whether he's still doing them or not, but nobody makes money out of turbines. The only people who make money out of hydro are the people who do the feasibility studies, people, that kind of thing. The actual people who are with the nuts and bolts never make the money. But if I move on to a case study, this is one we did. This is 100 kilowatt. If you look at the, can you see that? Don't know if you can see that. Okay, exactly. Because on my screen there's some pictures in the way I can't see. Head 140 meters. That's about that's about 459 feet. I looked it up. Flow 100 liters a second. Penstock length 900 meters. Capacity is about 100 kilowatts. Pipe goes up that hill, as you can see. Then it goes up a lot more hill than that. This was in the national park, Sea Tower. We had to build that turbine house, so it was faced up with stone and natural local stone, local slate, and all the rest of it. Also, noise is an issue with these. That's a pretty heavy built turbine house. It's a big Pelton in there. Well, it's a Pelton. You can't, a bit of a hum with it, but this back's making a fair noise. And one of the biggest transmissions of noise is in the tail race, the pipe which comes out back in the river. So we put it this way, we actually put it through stones at the end. So it's not enough to slow it down, but you see this is the outflow coming out of that turbine. So that one, and that's behind the turbine house. I don't know if you can see the pipe going in. This is preparing, there's bedrock there, preparing to put an anchor block in there. We always put there's many, many meters of concrete in that and steel just before the pipe goes in the turbine house. What you will, an issue you get with hydro is water hammer. You get a sudden blockage, you've got 900 meters of pipe full of water. I don't know how many tons of water there are in there, but it suddenly comes to a halt all at once. Something got to give, and it wants to all come down the hill. So it's very important we anchor it very well. Yeah. This is further up, on the same scheme, further up, you can see turbines down in that area, way down the hill. This is part of the trench. You can see that there's a cable coming up. This is a signal cable which comes up to the intake for the level sensor. This is a slide here. It was horrendous weather and horrendous conditions. This is a slide here of doing the pressure test. Before we actually cover the pipe in, we fill that with water, we test the whole pipe, checks there's no leaks on it. That takes a bit of doing. We join this pipe together, we get it in 12, on this particular case, I think that's about 400 mil pipe, 355, 400, somewhere like that, diameter. And it's butt welded. So you're familiar with that. It's a big plate comes down, a red hot plate, they shove the two ends together, two ends of pipe. It's timed and this plate comes out and the ends are shoved right. So it's just melting the plastic and shove it together basically. It's quite an expensive process. We hire people in to do it. And then we join several lengths together and we maybe pull 100 meters at a time down the hill. And then we join those lengths together with electrofusion joints, which are collars which will go over with terminals on them. And we have a special generator which there's coils inside this collar, and eventually and it welds the thing on where you are, kind of thing. This is back to the intake to remind you, this is the same site. Just to remind you, the pool created behind the intake, it washes over, it doesn't come under. Once the water's gone into the tank here, it's raining in like a thunderstorm in there. It's pushing loads of air into the water. That's one thing we don't want in the pipe. If you get bubbles of air coming down the pipe, it sounds like rocks coming through the turbine. You get cavitation, causes a lot of damage and really hammers the power. So it goes here sideways into a settling tank. Maybe in this case, it goes into two settling tanks, let the air bubble out. And as it goes down away into the penstock, into the pipe, we also have another vent pipe, which lets any further air which is accumulated out. It's very important as you're going down the hill. It doesn't have to go down a steady curve down the hill, but you mustn't, it'll go up and down, but it must never go up above the level or you're going to get trapped air in the top. That effectively reduces the diameter of your pipe, and you've got to stop that. So you mustn't let that happen. And this site, we had a lot of problem with. We spent a lot of money pecking rock out. It cost thousands of pounds, but we just had to do it. Makes it difficult when you're quoting for a job because you don't know what's under the ground. You think it's all diggable, and it isn't. And barring digging the whole thing up to start with before you do the quote, you've got to make a bit of a guess at it. That's the same turbine house looking in. There's the Pelton turbine there. I don't think I have any pictures of it inside. I'm not with me. I had to restrict how many I got. Just a few extra pictures I brought. This is a small little Pelton made in Peru, but we put it in. Single spear valve coming down there. That's a sort of old-fashioned type spear valve. It's got an electric actuator on it. This is again controlled by level sensor from the dam. The control panel will open or close this to keep the maximum pressure in. This is driving a permanent magnet generator, which goes through inverter back into the mains. It's doing about 4 kilowatts, something like that. It's been in since about 2014 or something like that. Client seems quite pleased. It's made in Peru, a little bit sort of old-fashioned, a little bit crude, but does the job. It seems to be fairly efficient. This is a repair we're doing to a turbine that we're putting, a Francis turbine I showed you earlier. As the water comes in there, round this scroll case, and in through, you can't see it here, but through guide vanes, which are fixed, which point the water towards the center, basically. Then within that, there's some more vanes, adjustable vanes, which work on an actuator. And these act like your nozzle. But unlike with a jet where you have one valve which opens and closes to adjust the nozzle, with these, remember, the water's going through all the vanes at once, all the way around. So you have to have multiple guide vanes all the way around, all linked to each other, opening and closing to let the water in. This is a very efficient turbine. The design of the runner, although the turbine was built in 2015, the runner inside, again, it's brand new, it was built then, but it was taken from a design from the States. This came from the States, this one. And the runner was a design from an American turbine company, a very good turbine company, very big in the States, in places like Pennsylvania and that. And you'll all know the name of making turbines. With Alice Chalmers, as you may know them, and Alice Chalmers, a tractor company. This you can see with the draft tube underneath. Obviously, the safety gear is taken off. There's a spider coupling there. Big bearing here. Massive thrust with this. One thing with a Francis turbine, you get massive axial thrust pointing in this direction. This gets pretty hot in here. We had to put an oil cooling. We were experimenting with an oil cooling system that it cool it down. Just getting a bit too hot. With a little turbo turbine, this is a spear valve that we make. When we make these turbines, the turbine we made, we don't actually make the runners, we buy them, but we make everything else. There's a spear valve. Now the spear, that's one in process of being made. It's not finished, but that fits. You might call them a nasal nozzle. It goes into a hole. The point of a spear valve is that this fits into a nozzle neatly here, sort of there. And when you want to open it, crack it open, unlike a tap or a ball valve, the water comes smoothly round all sides at once, and it doesn't impede or cause turbulence. So you get a very even flow. And then once it's been through the nozzle, which will be here, we want a rod of glass basically going out. We don't want the spray coming out because that's losing all its power. So you have to be very careful making spear valves. When this was finished, it was very smooth. This is still in the lathe there, that stage, as you can see. But that's a spear valve anyway. This one you just saw, that's the spear is right in the front there through a front support bearing. I've got some pictures of there. Front end of the spear will be looking out here. This is the front support bearing through a bronze bush there. this nozzle here is one of the nozzles. This will clamp onto the front. Notice that O-ring goes in this groove here to give you watertight seal. Quite a heavy made thing, that nozzle, because they has to take all the pressure. And the nozzle size is designed carefully to be right for that job, because the spear itself, from open to close, that spear doesn't move more than 15 millimeters maximum, maybe less. This is it. The spear comes, water's coming through. You see the water, that's running water there. You see the condensation on the outside. As the spear comes back through here, it comes through a bush there with a seal in there. Comes through a big bronze nut in there with a thread on the end, with a motorized actuator which will wind it in or wind it out. We have a, what do you call that? The thing which hits a limit switch at either end to tell it when it's open, when it's closed, etc. So that's the thing being wired up. I just thought I'd give you a shot of that. It's not just that we actually do something every now and again. That is the control panel for an off-grid hydro scheme. This is in Scotland, which is, there's no mains anywhere near this. Below the picture here, you can see, you can't really see, you can see a bit of spatter there, but there's a big row of batteries down here. Turbine charges these batteries. There's two water turbines there, actually. One's a 10 kilowatt permanent magnet generator, which we made. And the other one's a small miniature turbo turbine. Let's say it says large turbine, small turbine. You can see the controls there. It's on automatic or manual. If it's on automatic, the spear valve opens in or out as necessary to keep the pressure up. I could talk more about the electrical side if you're interested, because these off-grid ones are quite interesting.
Why have you got two turbines in this particular application? Is that because of high and low flows or something like that?
Basically, yes. What you'll find in practically any hydro situation, there's some months in the summer where there just isn't enough water to run it. Just about every hydro scheme you come across, you'll get, you know, in May, June, possibly July, the thing's not running. But this place was a domestic house where they needed power. Even if there's only a little bit of water, they needed to use it for some power. They get lights and TV, washing machine, they still need that. So that little turbine could be maybe doing 1 kilowatt or even 3/4 of a kilowatt when there was no other water about. And that's a lifesaver. I mean, you can run a house, if you're careful, you can run a house on less than 500 watts. You're storing it into batteries, still put the dishwasher on or the washing machine, whatever, when you want to, because it's getting stored up all the time. But during winter, you get most power. That's when you need it the most. You get a lot of heat out of it. So when the turbines charge the batteries, it automatically defaults to going into the heating system, into a bunch of immersion heaters inside a big tank. So this one as well. These inverters, this you can see the yellow inverter there. I think there was 2 of them, and there's about 2 of these red ones. These are what we call a grid tie inverter. The battery inverter, the yellow one, is what takes the battery power, takes up to 240 volts. These are, it's a special inverter, these yellow ones, that produces a thing called a mini grid. So it produces 240 volts, but it has the property in that you can put on the line 240 volts from a diesel generator or another inverter. This is a mains solar inverter or something like that. You can put it onto the output of the inverter. So in other words, it's like we're not just charging, we're charging the battery directly with a turbine in one instance, going in where the yellow one takes up to 240 volts for the use for the house, but you can put power into that anywhere on the system, somewhere on the other side of the house. You can connect solar panels to the output, to the mains, if you like. This yellow inverter will recognize it and put it back into the batteries, which is very clever. So it'll take power back at the same time as it's putting power out. or it can take power. It can be producing power, and the solar can add to it, and it'll use it. So it's the best of all worlds, really. Very clever. And they've got a diesel generator on the other side of this wall for when all else fails, and it will go through this system as well. It'll charge your batteries and go into the output, not just through the input, or into, which is what they always did. This can actually, you're actually putting power right onto the mains, which is clever. Those are all the slides I have. I've missed out a heck of a lot. I don't know whether anybody has any more questions.
Just going back to the spear valve.
Yeah.
And you're showing a picture there of one being made. Whereabouts is it? Is it on the next one? It actually showed that. That shows the actual. Yeah. Yes. That. Yeah. Yeah. It looks like it's been made in a obviously a collet on a lathe rather than just held in a chuck. So presumably it must have to be quite symmetrical in its design. Very.
Yes, that's a good point actually, because with these ones, there's two ways of doing this. We use a front support bearing. So there's a rear bearing where you see it coming out of the steel elbow. That's a bearing there because it's a bronze bush there. And the front end, it's on a long shaft before it goes into the nozzle. And we want it to go into that nozzle absolutely centrally so we get an even water flow around it. Because if the jet's corrupted, it's rubbish. So the front support bearing goes, around here, about where that collet is. And we have to get the thing absolutely concentric with that nozzle. And that actually makes the spear valve very tricky to make. You try, I'm sure you could probably do it a lot easier than me, but you've got an elbow, a stainless steel elbow there. Well, you know what stainless is like if you start heating the thing. And you've got to drill that elbow absolutely concentric with this point here. You've got to have a front support bearing, which is there. So your front support bearing's in there. That's held concentric by this casing. But the elbow at the back, it all gets welded up. Then you've got to drill it at the back. And once you've drilled the hole, you then have to weld in a piece of metal, if you like, which will carry you can't just have a hole in a bit of thin steel. You've got to have somebody to carry the bearing. That's going to be welded in. So you weld it in so it goes all over the place when you weld it. You then have to somehow keep this concentric with the thing you've just welded in. And they're actually quite difficult to do. Some people spin the whole thing on a lathe. Some people do it on a milling machine. We do it on a milling machine, but it's not easy, and every one is a fight. If we could get around it by, we have made some quite heavy jigging to do it, but you try welding stainless steel, even with a TIG, it shrinks all over the place. It's very, very difficult. So you're going to do your welding first, as you know, and then do your machining afterwards. But that's easier said than done. You try spinning that in a lathe, you can't get at it from the tool post because the elbow's spinning round. Tool post can't go near it. So you've got to do something from the tailstock. Really, you need a motorized rotary broach on the end of a tailstock or a milling cutter or something to do it right. Anyway, people know a lot better than me how to do that.
Does the surface finish need to be polished up as well on the end of the spear?
Not really. No, we usually get them more polished than that, but no, it's all right. You do like to get laminal flow if you can help it. Now, that was good enough, but that isn't perfect. That's quite good actually. That'll probably be good enough, but we like to get a little bit better than that. Usually this bit here, we like to radius that a little bit in that corner. But actually, in the grand scheme of things, with a thing like that, it really doesn't make any difference you'd ever notice. Just for your own satisfaction, you like to get it right, But if you see the jet coming out, if it's coming out like a rod of glass, you've got it right. If it's starting to look like a spray, you haven't got it right.
We've got another question from Henry Forth. what material does the front of the spear seal against? Is it a soft seal properly,
No.
or does the water wear that?
Actually, it's a good question. No, we actually use, I'll get it. This here, the nozzle here, that's what it seats against inside there. That's actually all made of 316 stainless. So we machine that seat just to give it a little bit of a flat surface to sit on inside there. And then this side of you can see just inside there where it sits. And then this is splayed out slightly here, so the jet isn't at risk of catching on the sides. So no, it isn't a soft surface. It could be, but we don't. And what you have to watch a little bit is that these schemes, you can get little bits of grit through, and if you're not careful, if you get soft material, you could embed bits of grit in it, and then it'll never close off. If that spear is, when it closes off, if it's a fraction, totally invisible, that water just piles through it, you've got, and then the problem is, if it doesn't shut off completely, you can hear the thing hissing. Not only that, it'll set the runner going as well. So you get the turbine going. And the big problem you have with turbines with these things is, with all turbines, is when you is getting the nozzles to close off enough so that the turbine doesn't run up past synchronizing speed, because you can't switch them on. If it's already doing 1600 RPM, it's not going to switch on. The control panel won't let it. But with these speed valves, we get them so they absolutely go off and you can't hear any water dripping. It's, we worked on that to get them right.
There was another question earlier on about pipe diameters. What sort of pipe diameters depending on the size of the installation?
Yeah. There are. I'm glad somebody asked that, because I've rather missed out the pipe thing altogether. What we call a penstock, the pipe, if you like. We use MDP or that kind of thing, black alkaline, basically. There's two big. There's SDR 17 or SDR 11. That tells you basically the wall thickness. SDR 17 has thinner walls, but it'll take up to 10 bar pressure. The SDR 11 has thicker walls, but it takes up to 16 bar pressure. And you can get other SDRs. You can get SDR 26, takes up to 6 bar pressure, things like that. You really want the thinnest wall possible that'll do the job, because the thinner the wall, the less the friction. There's no point in having something that'll take 16 bar pressure if you've only got 5 bar water coming down. You're just wasting space and you're wasting plastic. So we do a calculation. We work out how much water is coming down, and then we look at we have a computer program which will see how much. We'll try different pipe sizes in with the amount of water we got over the distance. So we've got 100 liters a second coming over 500 meters. We'll try a pipe size. We'll look at it on the computer program. Say it's got 100 liters a second, and it's got to come this far. And you type it in. It says you've instantly lost 30 meters in head. We try to keep it down to 5% if we can. Sometimes you can go over that. If you don't, we keep it down to 5%. But if it's going to be a very long pipe, to keep it down to 5% might mean we have to have such a big pipe diameter that the scheme's totally not viable. So we allow it to, basically we allow the water to come a bit faster down the pipe. The friction's higher. So if you like, the efficiency is less, but we're actually getting more power because we're just letting it run a bit. The pipe won't last quite as long, probably, if there's grit in it, but it's a very long-term thing anyway. So, but the optimum is about 5% losses. Pipe friction expresses itself as head loss. So if you have 2 heads, you look at the pressure gauge when the turbine stopped, and you'll have a dynamic head. So if it says, it might, if it reads in bar, it says 10 bar, it means you've got 100 meters head above you. The water in the intake is 100 meters above your head. Once you switch the turbine on, that's going to drop. So if it drops down to 9.5 bar, that's all right. we accept that, that's 5% loss. But if it drops down to 7 bar, 6 bar, you're really losing a lot of power there. Because remember, it's head times flow times gravity. So 100 meters of head times 100 liters, that's 10,000 times, we'll say 7, that's 70 kilowatts. If you have 95 times 10, that's 9,500 times 7 is a lot less than, it's a bit less anyway than 70 kilowatts, whatever 9.5 times 7 is. So, but if you're coming down to, 50% of that, you've lost 50% of your power, all for the sake of friction. That water's there, power's there available, but you can't have it because you put a pipe in that's too narrow. So people usually, especially people with micro hydro things, they work out the cost of things and they think, oh, that's fine, I'll put I'll push the boat out, I'll put a 50 mil pipe in. Usually, even a tiny hydro scheme is going to need a 4-inch pipe, So, and this is where a lot of money goes. The average micro hydro scheme pipe length is somewhere between 300 and 400 meters. If you got a very steep site and you've got less than that, well, that's good. But if you've got much longer, that's no good. Talking about length, we have sites where I showed you this site, Blencathra here. That Francis turbine there is 2.6 kilometers away from where the power is consumed. And to get the power back down, obviously you're going to lose all. To put the cable in, this was in 2013, I think this went in. I think the cable for that was going to be something like £35,000 for the cable to get it that distance, to get big enough cable that carried that power at 415 volts. So we went down a different route. We got medium voltage. We put transformers in. We got some transformers, maybe put up to 3,300 volts. And then we took it down the road and then back down to 415 the other end. We did the whole thing for about a third of the price of what it would have been if we just bought the big cable to do the job. Especially now, copper is just out of this world, the price of it. But you can use, high voltage cable. You reduce the amps right down, so you get a little bit loss of efficiency on because the transformers give out a little bit of heat, but you can put that heat in a building where you can use it. So it's nothing really.
On pipes then, so just to summarize there, basically the longer you run and the more flow you get, the bigger the pipe you need.
Absolutely, yes.
Okay.
It's as simple as that.
Yeah. Another question again from Henry about getting pipe to site and also the lengths of sections of pipes. And you briefly mentioned about the joining process. Could you just say a little bit more about that joining process, this welding process?
Yeah, if we big scheme, such as this one's quite a big scheme, this one here, we get the pipe butt welded. So we get, we've got a 12 meter lengths of pipe or whatever they are. And this company comes with a machine and you need a big digger to put these bits of pipe, mount them on this machine. Imagine like a sort of a table thing, and it clamps it down. It moves the pipes. First of all, they scrape the pipe. There's a gadget which takes a tiny skim of plastic off all the way around the pipe to get it, to make it more grippable anyway. And then the two pipes are shoved together, hydraulic things, push these two pipes together like this, but separated by a plate, just like a big flat plate. But this plate is a heating plate. And then a timer comes on and heats this for a set length of time. And then it pulls the plate out and then it shoves the melted pipes together for how many minutes it is. Then you've got it set and then you're joined. That's the pipe welding thing. But that has to be done in one place. You don't move that around the site. You set that up usually with a tent over it. You need a big sort of 13-ton digger to put these bits of pipe on it. You need another digger pulling the lengths of pipe away as they're joined. You're getting a bigger and bigger length of pipe. So you maybe get 100 to 150 meters of pipe all in one length, which you've got to drag away. So you need a few men on the job. The other system we use is electrofusion joints, which we use on this anyway. When we join those long lengths together, eventually, when they're in the trench, we put these things, they look like a collar, which, you know, you shove one end into one pipe, the other one goes into the other. It goes over either end, and it has two terminals on it, and you have this electrofusion gadget thing on a generator. You join it on, you set the little computer, and it puts electricity into it, because these collars have electric coil going through them, and it basically cooks the pipe inside there for so many minutes, and then it goes off, and you mustn't touch the pipe, let it cool for so many minutes, then she's strong again. They're very good. They're quite expensive.
Another question from Jin Lines. What sort of filter do you install at the inlet, or is it just that screen?
That screen, yeah, that's a one we saw. There was a 1 millimeter screen. That's well enough. Sometimes people go for 2 millimeter. With low head turbines, we usually have a much coarser screen than that. We don't use this type of screen on low head turbines. Anybody guess why?
You just get too much aeration, and you can't get that aeration out before it gets to the turbine?
No, that's not the real reason. The real reason is that when you look at that, that is about at least 4 feet in height, top to body. With low head, you don't have that to spare. You might only have a total of 10 feet head on the whole scheme. So you can't afford to use a Coanda. Also, these Coanda screens, that one there is handling 100 liters a second, and it's about, I don't know how wide it is, about, we'll say it's 5 feet wide or something like that. But the low head schemes often handle a lot more water than that. You're going to have to have a much wider one. So they're going to be very expensive, but you're losing the power, you're losing the head. So you're not trying to force the water through a narrow spear nozzle. So we're usually going through, as you say, with the Francis or the propeller, you've more room to get the water through, so you don't need to be that coarse. Some of these turbines, we'll even take fish through them without mixing them up too much. But the environment agency usually want you to put something like 5 millimeter screens on to keep fish out if it's a problem.
Right, I can't see any more questions in the chat. Does anybody want any more questions answered? Right. I've actually got one more final question coming from Sarah. Just saying, could you explain a little bit more about the low to high voltage transformers?
Yeah. Well, they're just transformers, basically. We get them specially made, but as long as we spec them, we put a little domestic system. Well, actually, with a little hostel, we put one in, and the electricity had to go. It was only doing about 3-4 kilowatts, but they had to transfer the electricity for about a mile, a bit less, before it got back to the ranch, if you like, and into the batteries there. So we used conventional armored cable, and we put it up to 800 volts. That made all the difference. And that's running fine today. So 800 volts, but with bigger schemes, we'd go a high voltage. The one I told you about, the Francis turbine, that went 2.5 kilometers. So we put it up to 3,300 volts, which I think is the same as they use down the mines. And the cable, you use a special cable for that. You buy, I don't think it's called high voltage, I think it's medium voltage cable. That stand to be correct here. And you've got to have specialist connections on it, and there's specialist protocol for using it. And when you're using in that kind of voltage, you really got to watch what you're doing, because it jumps around a bit. And if you get a belt off that, you usually probably aren't going to wake up again. So we're looking at one at the moment to do, and we're looking at, that's going to be 11 kV. So that's hotter yet. And yeah, you just got to, when you're doing it, you have to have the guy that's in charge of the connections has the only key. Everything's locked, and the only one key will, you can't switch it on at one end by mistake while the other fellow's working at the other end, because he has the only key. And I can't remember how it works quite, but it's sort of a fail-safe system because you just don't get a second chance with that. And as I say, as you know, electricity with that kind of voltage can jump, and you don't want to even be near it. So I don't know whether that's about all I know about transformers. So I'm sorry if I didn't answer any more on that part.
Another question from Eric Murray. How much of the system, such as the one in your case study, costs from design all the way through to a working system?
Now then, oh God, I'll try and remember that. I'm going to guess it because I can't actually remember. This is a bit of a guess because I really don't remember the figures on that. I would guess about 400,000 maybe, something like that.
That's quite a considerable investment then, isn't it?
It is, that's what's about £4,000 a kilowatt installed, which is, it was maybe less than that. Honestly, you know, I'm really just, I should know that, but I just completely forgotten it. The small scheme, domestic schemes work out pretty expensive. The feed-in tariff was what made them viable in the short term. The thing about hydro is that yes, it's expensive, but it is there for a long time. You know, we use stainless steel runners. There's no reason why these systems can't keep going on and on and on. Whereas wind turbines, you know, you get your 20 years, maybe a bit more out of them. But then you can keep repairing them, I suppose. But you have some fairly major costs on them. Whereas a hydro, give you an example, one near us, just a mile away from here, we put one in on a farm in 2015, and he had a head of 450 feet, and he's got 9 liters a second, which is not a lot, but he gets something like 8.7 kilowatts out of it. Penstock length's about 770 yards, 770 meters. The internal diameter of the pipe is about 4 inch. Cost him, we built him his turbine house and everything. We did everything. We even made the turbine. We didn't make the control panel in this particular case because we don't do everything. But we got cost about £50,000. But the first year benefits here, we had a walk round with the local public walked around it. So I can give you these figures because it's in the public domain. And he said in the first 18 months, it had yielded about £10,000. The cost of 50,000. So that over a year, I suppose that's about 6.5 to 7, somewhere around there a year. Now that is made up of the fact that he was getting 19 pence a kilowatt hour for the feed-in tariff, and the feed-in tariff is what you get paid for every kilowatt hour you generate, no matter whether you use it or what, or give it to or sell it to the mains. If you sell it to the mains, then he would get probably an extra 5 pence on top of that. So first of all, you get the feed-in tariff, which is a silly name because it's a generating tariff. You don't have to be connected to the mains to get the feed-in tariff. You have plenty off-grid ones getting feed-in tariff that are nowhere near the mains. So you get every kilowatt you generate, you get the feed-in tariff. You then get to use that power after you've been paid for it. And any you don't use will go back into the mains, and you get paid for that, 5 or 6 pence. They're not as generous as that now. You don't get a feed-in tariff anymore. You can still get paid for exporting it, and you get to save whatever it costs you to buy it. I mean, the cost of electricity now, it's getting to the point where it's going to become more viable to have these schemes even without a feed-in tariff because you're paying so much for it in the first place.
That comes to another question John Goss put in there is, do you think that we could utilise our rivers at regular points in this country to generate for local communities?
Yeah, this is going to be down to the Environment Agency. You've got, if I just stop the share. No, better. The Environment Agency will govern what you can do with these rivers. They're very sort of cautious because they don't want to upset the fishing or anything like that. And they don't want you damming any rivers, no major rivers. You just won't get the dam there. If there are weirs there already, you're lucky. You should be able to use them. There's a lot of, you'll need fish passes and things like that, so fish can go up and down. Also, if you're using it on a reasonable sized river, usually there isn't a lot of head there. You know, you might be talking about low head skim. If there's a weir there, you might have 6 or 8 feet of head, which is good, but you're going to have to use a fair proportion of that river. In parts of the southwest, you have quite a lot of big, wide valleys with quite biggish rivers where you can use low head hydro. I know I've been around in Pennsylvania there, they have a lot of big wide rivers, wide valleys, not a lot of height. And they have these quite old big Francis turbines, maybe 5-6 feet across, the runners on them. And they'll have a pole coming up out of the shaft, coming right up out of them to a turbine house on stilts well above it, because to get away from the floods. And these are owned by Mennonites, which is the same as the Amish without the beards. And the power coming out of these will go along, they'll take it along to the farm buildings, they go along some gnarled old tree they've jammed in the ground, and then another one and another one. But they're very clever people, and they run these places off these. There's a lot of these about. So, but I said that to demonstrate the fact they're doing a lot of low head stuff over there. The American full of hydro, much more so than here. But the southwest of England is always been a good site for hydro. A lot of low head stuff there, a lot of old mills, a lot of potential sites. But the key thing is being able to get that water out the river. And if you can't put the dam across, there's another thing you can do, especially if you're on a bend of a river. If you're on the outside of a bend, you don't take water off the inside of a bend because it silts up and it'll block up. You put it on the outside. If you put a wall there with some vertical bars on it, you can persuade water to come through those bars and drop into a pit if the landscape is okay there. And then once you got in the pit, you can do what you like with. As long as you've got somewhere for the water to fall to, you've got it. And so you don't have to dam the water. But I don't have a lot of hope for a massive amount of hydro potential in these rivers, unless you have rivers where it's fairly steep. One thing with these high head schemes, there isn't a lot of biological life in them. So you get permission fairly easy to get hydro on them. But if you're down some limestone river and, the river Kennet or something like that, there's no way they can let you put a turbine on it, I don't think, because there's a massive amount of flora and fauna in those rivers.
And then probably one final question now from Will Flynn, just to expand on the lifetime of the systems. You mentioned that wind power is maybe 20, 25 years and the hydro is a lot longer. What sort of time scale are you looking at?
For the hydro turbine itself, the turbine runners, we're using cast stainless steel runners. They just they last an awful long time. And I think I've seen ones which have been over 50, bronze ones over 50 years old. They're getting a bit thin, some are getting holes in them, but you can replace those bits. You can replace every bit on a hydro turbine. The runners are usually the most expensive bit, but they're not that far out. But the other things, the generators, keep the bearings all right. If your system is connected via inverters have a life with them, I would think 12 years or more for inverter. They're quite expensive, but main thing goes with inverters is capacitors. And if you keep an eye on them, you can replace capacitors. So the other thing about inverters is they tend to be, nowadays, they're really all very software driven. But you know what this stuff is like? The software goes out of date and you don't adjust it well. Your stuff, it's a bit like having a computer from 2005. You just can't do anything with it now. So that's something to watch. That inverter I showed you, the yellow one, which is a very clever one that produces a mini grid. It tells you when to charge it tells the generator when to start up, when the battery's charged, it switches it off, and it's all very clever that way. But the newer version since then, they've taken the screen away off them. And the only way you can communicate now is with an app on your phone, and it has its own Wi-Fi. You try getting your phone to actually connect with it. You know, I told them, I rang up the people in Germany. I said, I hate these things with a passion. He says, yes, I know, we have had a lot of complaints. I says, well, change it. But they haven't done, they're still doing it. The trouble is the people designing these are geeks. They're not real people, they're geeks. They're not the people who have to use them. If you want to know how far charged your batteries are, you need to run in the turbine house, see if we've got enough power, you know, for some reason, or how's the batteries doing, or what's going on. You can't run in and tap the screen and have a look at it. You've got to get a phone out, get the phone and get the password and all this nonsense. Sorry, I'm stepping off on a rant there. I shouldn't talk about that. But I'm not a big fan of inverters, but we do use them.
Okay, right. You haven't covered about screw turbines at all.
Turbines, yeah. We've never put any in, but we've looked at them and we deal with a company that does them. Don't know a lot about them. The fish people like them because fish can go down them without any problem. You know, they don't get minced up. The downsides of them, there's quite a lot of wear on the bottom bearing, which tends to be a cutlass bearing, which is a rubber bearing basically, which they use on boat propellers. That's one thing. They're very, very slow running. So they've got to go through a gear system above the thing. So on top of this thing, you're always going to see this great big box with all the gears in and that. They're pretty visible. An advantage of them is that you can dig the site out. You basically drop a thing in as on a skid unit. You've got it there. You don't have to have any pipe to it. Don't know. We were looking at putting one in this last back end. I was going to get another company to do it because I didn't really want to be involved with them. And I was quite pleased not to. I mean, if people are worried about aesthetics, you can't put them in really. We were looking at them in some sites in the south of England, and we don't really do the south of England, but this is when we did. They weren't going to wear them. And when you have to gear anything up from such a slow speed, you've got big wear, big losses on your transmission. But having said that, they have the uses, and I'm not going to knock them. Every turbine has its use for a different reason. And there's plenty of screw turbines about.
Okay, right. I think we've got to maybe finish there. There's no more questions at the moment. You've been talking for a long time now. I think a lot longer than you anticipated.
I've just waffled mainly.
I've definitely found it interesting. So, have you got any more comments, Simon?
Well, no, just to reiterate what you've just said, really, just to say, yeah, really, really interesting. Thank you very much there, Miles.